So good day. In this class, we are going to discuss another modern material, that is Maraging steel. So this Maraging steel can be used in high-end engineering applications like aerospace or nuclear reactor or high tooling area. Everywhere we can use this Maraging steel. So here in this class, we are going to discuss this type of modern material, Maraging steel. So from the name itself, this is a steel. So we know what is a steel. Steel is an alloy of iron and carbon. But compared to the ordinary steel, low carbon, mild steel or high carbon steel, the percentage is vary between 0.2 to 2 percentage. But here in this marine steel, the main characteristic is that it has very low percentage of carbon. That is very important. For ordinary steel, there will be a higher percentage of carbon, up to 2%. But here in this marine steel, the percentage of carbon is very low. That is only less than 0.02%. So that is one of the important characteristics of marine steel. And next one is this marine steel. Even the carbon percentage, the alloy element carbon percentage is low. But we use another alloy elements such nickel, cobalt, molybdenum, and titanium, etc. For making this marine steel. And the percentage of nickel is around 18 to 25 percentage, and cobalt, molybdenum, titanium also used as a alloy elements to improve the properties of the marine steel. So this is a steel. Marine steel is a steel with a very low carbon percentage, but with a very high percentage of nickel, cobalt, molybdenum, and titanium alloy elements. So that is the arranging steel. And so that is the first part. We call this as a steel. Even and the percentage of carbon is low, but it contains carbon. That is why we call this material as a steel material. And next term is maraging. What is maraging? Maraging is actually a combination of these two terms, martensite plus aging. So we take the three letters from the martensite and the second word aging. So martensite plus aging is called maraging. Okay, so you know what is martensite from the iron carbon equilibrium diagram. How this martensite is produced. Martensite production can be explained from the TTD diagram. First we cool into austenite temperature range. So this is the austenite. So we have to first we heat into austenite temperature range. So this is the austenite transformation temperature lines. So we heat above these two temperature lines, we got austenite. Okay, so after the formation of austenite, so this is the line showing the austenite phase. So above this line, this is austenite. Then we cool this austenite phase by very rapid cooling. Okay, next we do rapid cooling from the austenite stable state. So by rapid cooling, we reach MS where the martensite starts to form, and when we reach MF, the martensite formation will complete. So by rapid cooling, or another term is called quenching. So austenite is rapidly cooled or quenched to produce martensite. Okay, so we got martensite, and this martensite formed in an ordinary case, the martensite formed is very hard and brittle, so we cannot use this martensite for the application where the toughness is involved. Because of the brittle nature, there is a chance for the breaking of these martensite because of the brittle nature. So we cannot use martensite for different applications in modern engineering conditions. Okay, so but here in the marine steel we use very low carbon percentage, less than 0.02%. So even the process is same, but in marine steel the martensite produced will be soft. It is not very hard because of the very low percentage of carbon. So the main agent for improving the hardness is carbon. So in the maraging steel, we have only very low percentage of carbon. So the result, even after quenching process, the process is same. After the quenching process, the final product or final martensite will be soft. So that martensite is called lathe martensite. That is called lathe martensite because here we use very low percentage of carbon. Okay, and second time is, so we got a martensite. Specifically, we can say that is a lathe martensite. So at the end of quenching process with a very low carbon content steel, we got a martensite, lathe martensite at end of this process, quenching process. And this next term is called aging. So we already studied the precipitation hardening. So that is another term of aging. What we do is that after the formation of this martensite, we increase the temperature of the martensite. So here we can see here at this point martensite is formed. Then we increase the temperature of the martensite. Then we maintain that martensite or lathe martensite at that higher temperature for a long time. So here this is the aging time. Okay, so we maintain this lathe martensite for at a higher temperature for a long time, and that process is called aging. So during this process of aging, some secondary precipitates will be formed uh, inside the primary phase. Okay, and at the end of aging, we got Maraging steel. Okay, at the end of aging, we got Maraging steel. So this is the aging process. This is the first stage that is quenching. At the end of quenching, with the low carbon steel, we got lathe martensite, and this lathe martensite again heated to around 500 degrees Celsius, and we maintain the lathe martensite for a long time at a 500 degrees Celsius, and that process is called aging. At the end of aging, we got Maraging steel. Okay, so that is the two terms indicating in the Maraging steel, martensite plus aging. So this is the very important characteristics of a Maraging steel. We kept a very low carbon content in the Maraging steel, and we maintain this low carbon content in order to prevent this formation of titanium carbide, TiC. Because here we use titanium as an alloy element, and which give different which improve the properties of the Maraging steel, but there is a chance for the reaction of titanium with the carbon. So in order to prevent this formation of titanium carbide, we maintain low carbon content in the Maraging steel. So this is what we discussed. The martensite obtained is soft due to low carbon content. So in this case, this is the TTD diagram, secondary phase and primary phase transformation. This is the TTD diagram. So this is the alternate temperature, stable alternate temperature. From this, we rapidly quench the low carbon steel. This is very important. We got only soft martensite only by using low carbon content. If we use high carbon content, then we got very hard martensite that we already discussed in the third module. So if you want a martensite with a soft or ductile nature martensite, then we have to use a low carbon content steel. So from the austenite, low carbon content austenite, it is cooled rapidly. We got a soft martensite which is called lathe martensite. Another name is called lathe martensite. Then what we do, we then after that we heat into 500 degree, around 450 to 500 degrees Celsius. This is 500 degrees Celsius. Okay, 500 degrees Celsius. Then after that we kept this lathe martensite at 500 degrees Celsius for a long time. So this process is called aging. This is called aging. Okay, aging. And at the end of the aging process, we got, then after cooling, we got, at this point, we got Maraging steel. Okay, so what is the advantage of developing such a Maraging steel? The main advantage is that at the end of this martensite formation, at this point, we got soft martensite. Okay, at this point, we got soft martensite here. So in this point, the material is very soft. So we can and this soft material allow cold working of alloy to desired shape. We can make any desired shape at this stage, because at this stage it is very cold. So we can make any connecting rod, we can make any die, and we can make any tool. It's very easy because we can make any, we can convert the material into any shape because of the soft nature or ductile nature of the martensite at this point. So at the end, we make a product. For example, a connecting rod is made at the end of this process. Because this is a very soft material, we can with a very low force, by applying very low amount of force, we can convert into desired shape at the end of this process. Then after that, the final product is aged. Okay, the final product is aged. What happened at the end of the aging process? The soft lathe martensite is converted to Maraging steel, which has very high strength and hardness. Okay, and that is the after cold working. This martensite is subjected to artificial aging. This is artificial aging at 500 degrees Celsius. So here at this point it is very soft, and during that time we make a product. We convert the material, raw material into a product, and that product is subjected to aging process. That means we kept the material, the final product at 500 degrees Celsius for a longer period of time. Okay, so at the end of this aging process, due to aging, strain-induced precipitation hardening occur due to the precipitation of intermetallic compound. So during the aging process, there will be the secondary phase, precipitates are formed. Okay, intermetallic compounds. These precipitates are nothing but it is an intermetallic compound. We studied the intermetallic compounds developed in the iron carbon equilibrium diagram. So this is a cementate, that is an intermetallic compound, Fe3C. So similarly, an intermetallic compound is produced, and this intermetallic compound is precipitated in the primary phase. How this intermetallic compound is precipitated? For example, this is the primary phase. So for example, this is the grains, different grains, and this is a primary phase. Okay, and the intermetallic compounds are, so such type of different intermetallic compounds are produced. We will discuss about that. This is the secondary phase intermetallic compounds. Okay, so this secondary intermetallic compounds actually developed during the aging process. Okay, and this secondary intermetallic compounds hinder or prevent the dislocation motion. Okay, to prevent the dislocation motion, thereby the strength and hardness of the material will increase after the aging process. Okay, so thereby we can improve the strength. So that is the process for developing maraging steel. So that is we already discussed. It's a high alloy with the nickel and cobalt molybdenum, and we may get a strength up to 2400 megapascal. It is almost 10 times higher than that of ordinary steel. Okay, so that is the importance of this development of maraging steel. But the main problem of the maraging steel is this one. This we need nickel, cobalt, and molybdenum, because the nickel, cobalt, molybdenum actually produce these intermetallic compounds. Okay, the secondary phase intermetallic compounds actually developing the strength and hardness of the maraging steel. For making this intermetallic compound, we need nickel, cobalt, and molybdenum. We know this nickel, cobalt, molybdenum, etc., titanium, etc., are very expensive, very costly material. So the final maraging steel is very costly. So we cannot use this maraging steel for ordinary application, but we can use this maraging steel for high-end applications like your aerospace field, or to make high-end toolings, etc. We can use maraging steel. So in the final product will be very expensive. That is the main problem of maraging steel. So these are the advantages of maraging steel. It has a very high yield strength. It's a very comparable with the ordinary steel, and it has very high weldability. Weldability is high because of the presence of these intermetallic compounds, and the nickel, etc., alloy elements, cobalt, molybdenum. We can increase the weldability of the material. So we got high strength weldable joints when we use maraging steel. Another one is high fracture toughness because of the presence of this nickel and titanium. The fracture toughness also will be high, so it has a capacity to carry high impact load. Okay, and intricate shapes can be easily machined, and that is also discussed. Before aging, we can machine to any shape because that is a very soft condition. So we can machine to any shape, and then we can age to high strength and hardness. So that is about uh, the advantages of the intermetallic compound. So this is a carbon free or small amount of carbon is used in this Maraging steel, and how this strength is developed by the presence of precipitation of intermetallic compounds and Martensite transformation. The strength is developed in the steel. And what is the percentage of different alloy elements? We use nickel around 18 to 25% nickel is used, 0 to 18% cobalt is used, and the percentage is given in another table. So these are the different grades. Okay, different grades of Maraging steel, 200 grade, 250 grade, 300, 350, different grades. And commonly we use 18% nickel for making the Maraging steel, and see the percentage of molybdenum, cobalt, titanium, and aluminum. So these are the main alloy elements used, but this one is very essential, nickel. Okay, nickel based Maraging steel. So these are the alloy elements used in the Maraging steel. And these are the intermetallic compounds precipitated in the during the aging time, and this intermetallic compounds actually prevent the movement of the dislocation. Thereby, strength and hardness can be improved on a Maraging steel. So these are the grades, and the carbon content is very low, less than 0.2%. And this is very lightweight structures can be made with very high strength and hardness, toughness, etc. That is one of the important application of the Maraging steel, and this can be used in aerospace area. And there are different applications we can see in the missile, load cells, helicopter flexible drive shafts, jet engine drive shafts, landing gears of the aircraft. Everywhere we can use this Maraging steel because of very high strength and toughness. So toughness is an important property that resists the impact load. Okay, and in the tool manufacturing industry also we use Maraging steel. We can make different toolings using Maraging steel. So it has a good strength and toughness. There is no conch cracks problem, because during the conching of ordinary ordinary steel, when we conch into martensite, there will be a chance for the formation of crack, but such problem will not be here in the formation of Maraging steel. And good dimensional stability during the heat treatment. Even after formation of the Maraging steel, we make a product. After the end of the late martensite formation, we make a product. Then we do aging. So during the aging process, there is no variation or very little deformation or change in dimensions during the aging process. So good dimensional stability will be maintained during the heat treatment process. Excellent workability and machinability, and they can be cold work as well as hot work. And there is no danger of decarburizing during the stage of thermal process, because we use very low carbon percentage. So there is no chance for such a decarburization during the thermal processing, and it has very high weldability. And how this Maraging steel form with the very high strength and hardness, because of the two important steps or formation. The strength is developed in the Maraging steel. First one is the formation of lithium martensite, and second one is the precipitation of the lithium martensites in the primary phase. That is the two reason for the development of strength and hardness on the Maraging steel. So for first, I already discussed how this lithium martensite is formed. The iron nickel martensite structures form when the iron nickel alloy is heated to 800 degrees Celsius. So I already discussed about that. So here, this is a CCC diagram. CCC diagram. Sorry, TTT diagram. This is the TTT diagram, and this is the alternate temperature range. Alternate temperature range. Okay, so here from this alternate temperature range, we cool into martensite temperature range, MS, below MS and MF, and we got martensite. And this martensite is so this is here in this alloy composition is 18% nickel, and it's less than 0.02% carbon, etc. So when we first we heat into 800 degrees Celsius, we got this point, and from the alternate temperature formation temperature, then we cool into 300 degrees Celsius where martensite is formed. Okay, so iron nickel martensite, which is called lithium martensite, which has BCC structure formed by diffusionless transformation from FCC austenite. So we know the austenite has a FCC crystal structure. Here it is FCC, but when we quench, the FCC changes to BCC. Okay, so we got BCC, lathe, martensite at the end by this rapid cooling. Okay, and this lathe martensite is not hard. That is very important. This is not very hard as that of ordinary martensite. If we use a 1.5 percentage of carbon steel from austenite to martensite, we cool from austenite to martensite, it will be very hard. But here we use very low carbon percentage austenite. From a very low carbon percentage austenite, we cool into martensite temperature range. Then only we got lathe martensite. And of course, the nickel also is an important part for formation of the lathe martensite. Okay, and this lathe martensite is not tough and ductile, but it is very soft. Okay, it is soft when compared to ordinary martensite. And after that, then martensite is formed by rapid cooling. If we this percentage is important, 23% nickel. If we use a higher percentage of nickel, it may chance for the formation of tinned martensite. Okay, that is not a desirable one. So we need lathe martensite at the end of quenching process. So we got lathe martensite. This is the lathe martensite structure. Here we can see packets and blocks arrangement of lathe martensite. Okay, so this is another one. So it has a BCC crystal structure, and but not without any tuning. There is no tuning, and it is relatively soft. We can see the hardness, only 30 HRC hardness. So it is almost ductile and which is missionable. Okay, so we can convert in this lathe martensite to any product. Okay, we can make connecting rod or tolling or gears. Everything can be made from the lathe martensite because of very low hardness. So the low hardness martensite formed after annealing has a hardness value only 30 to 35 HRC. So which is very soft. Intricate shape can be machined in soft conditions. So at this stage we can make any product. Okay, and then it can be hardened as there is only a slight change in the dimension during the age hardening. So when we make a product at this point, after any heat treatment, there is a very light change in the dimension. So this will not affect the dimensions. Okay, the precipitate particles are of lattice size comparable to that of martensite matrix and cause little distortion of the matrix. So this characteristics together with the absence of carbon allow the steels to be age hardened to very high strength level while minimizing the change in shape of the part being hardened. So this lattice size is very comparable. This precipitates formed during the aging. The lattice size is very comparable. So this will not change the dimension of the final product. So first the lathe martensite is formed with a moderate hardness compared to ordinary martensite. After that, the lathe martensite is so we make a product at this stage. Then after that, we reheated to 500 degrees Celsius. So we reheated to 500 degrees Celsius. So from this one, lathe martensite. Okay, and we maintain the at this temperature for a longer period of time, maybe 1 to 6 hours. So this is aging. We maintain at that temperature. This is 500 degrees Celsius. This one is 500 degree Celsius. We maintain at the higher temperature. Okay, so by the aging, this minimize or eliminate the reversion of the martensite into austenite. So this martensite will not reverse into austenite stage by the diffusion process. Okay, so that is the importance of aging process. So during the aging, ordained precipitate phase of nickel-rich intermetallic compounds. So during this phase, nickel-rich intermetallic compounds, we already discussed there are two intermetallic compounds will be formed, and these intermetallic compounds precipitate in the primary phase during this aging process. So at the end we got, and then again we cool to room temperature. At the end we got martensite. Sorry, Maraging steel. Okay, so during this aging process, this is actually happen when we take a grain, this nickel Na3MO and this Na3PI. This intermetallic compounds. This intermetallic compound starts to precipitate in a fine sized. This is a very fine sized. Precipitates are formed in the grains. This precipitate actually hinder or prevent the dislocation motion. Thereby the strength is improved. Okay, so see this Na3MO precipitates. So by introducing this Na3MO precipitate, this blue color is this one. Okay, this actually develop a strain field around the secondary phase Na3MO. Okay, this strain field actually prevent the dislocation motion. So it's very difficult to make a motion or we have to apply more energy for the dislocation motion because of the presence of this intermetallic compounds. Okay, so that is the precipitation or aging of lithium martensite. So by this these two process, first the formation of lithium martensite and second one is the precipitation of lithium martensite. We got higher strength in the Maraging steel. And this is the aging time. The aging time is very important because when we draw a graph between the hardness and time, this is hardness and this is time. Okay, so when we draw a graph, initially after consume we got a lithium martensite, and the lithium martensite during the aging the hardness and the strength will increase, and which reach a peak value, then it will decrease. So longer aging time or commonly we use 1 to 6 hours for aging, but if we increase the aging time, what happen from the peak hardness, it again decreasing. The hardness is decreasing from the peak. So we have to maintain a particular aging time. Okay, this is the aging time for maximum hardness. Okay, so this is called aging. This is called aging, and this region is called overaging. This is called overaging. So this overaging actually reduce the strength and the hardness of the material. Okay, so we have to, by experiments, we have to find the aging time for maximum hardness of the alloy material. So effect of aging, see this at the end we can see there is a decrease in hardness. Okay, this is the different aging of the Maraging steel at a different temperature. Okay, we can use 500, 480, 425, etc. So overaging is not a desirable one. And these different alloy elements are used: titanium and molybdenum, moderate hardener, copper. So all these things, titanium, copper, molybdenum, everything produce these intermetallic compounds. That is actually the secondary phase precipitates, which actually used to improve the strength of the Maraging steel. And these are the effects of different alloy elements: nickels, alloy, titanium, aluminum, cobalt, molybdenum. Everything is used as a alloy element for the Maraging steel. Okay, so this is the yield strength and the tensile strength and the hardness values. So we know we can see the increase in hardness of different grades. The grades is based on the percentage of molybdenum, titanium, etc. We can see this. The nickel is same, but this percentage is vary. Thereby we can make a different grades of Maraging steel. So this is the comparison with the ordinary steel. So this is the 300 grade Maraging steel, 250 grade, 200 grade Maraging steel. So see this fracture toughness. Toughness is very high for Maraging steel. This is ordinary steels. Okay, 4330M grade, the 300M grade, H11 grade. So this is ordinary steel, and its strength also given. So here we can see it has very high toughness. And for 250 it has medium toughness and tensile strength. So compared to conventional or ordinary high strength carbon steel, it has this area showing the Maraging steel. Okay, it has very high strength and um, toughness, even hardness also. So that is about Maraging steel, and these are the two important characteristics. It has very low carbon content, and initially the lathe martensite is formed. Then during the aging process, this lathe martensite is by the precipitation, the strength and toughness increased in the Maraging steel. So, but the main problem is that it is very expensive. These alloy elements, nickel, cobalt, molybdenums are very expensive material. So, we know this is almost this for titanium, even titanium is almost 30 percentage composition in the total material. So, in this 30 percentage composition is very costly. That is why the Maraging steel is also expensive. So, we use only in the high-end applications like aerospace and tooling, etc. Okay, so thank you. That is about Maraging steel.